Hello friends, welcome to Civil Master. In this video I am going to discuss about the design process of simply supported RCC beam by limit state method with the help of an example. So let's get started. Guys, as you can see here, this is our beam and this is the UDL acting on the beam whose magnitude is 25 kN per meter, and the grade of concrete and steel are M30 and Fe 415. It means that the characteristic strength of concrete is 30 Newton per mm square and the characteristic yield strength of steel is 415 Newton per mm square. The effective span of the beam is 8 meter. Guys, the effective span is that span of the beam at which the load is actually acting on the structure. It is called the effective span. So let's get started the stepwise calculation of design process. So guys, our step 1 is to find out the features of beam. Features mean that the width and the effective depth of beam. So in the case of simply supported beam, by the IS code 456, we have the ratio, the span by depth ratio is equal to 20. So here we have the span L is equal to 8000 mm. So we can find out the effective depth. So 8000 mm upon 20 is equal to D. So here we have 400 mm. So here we have the assumed effective depth is 400 mm. Guys, this is the assumed depth, and actual depth we will find later with the help of moment of resistance. Till then we will use this depth. And for the calculation of width of the beam, we will use this depth. According to the IS code, the width of simply supported beam should lie between D by 2 to D by 3. So B is equal to 400 upon 2 to 400 upon 3. So it is 200 to 133.33. So let's we take the intermediate value. So we are taking B 250. Sorry, 150 mm. So it is our assumed width. Now going to the step number 2, which is loading. Guys, usually loading is of 3 kinds. One is superimposed load, second one is live load, and third one is dead load. So superimposed load is that kind of load which will act on the beam after the construction, after the structure is ready to use. It's like our human load, etc. And live load consists of the loads which act on the beam at the time of construction, just like crane load, instrumental load, the loads of labor, etc. And the dead load is the self weight of the structure, and the self weight of the structure is calculated by the width into overall depth into density of concrete. And the density of concrete is approximately is equal to density of concrete is approximately 25,000 Newton per meter cube. But in our question, we already have given the value of total load, which is 25 kilonewton per meter. So there is no need to find out these loads separately. So here we have the total load. Now going to step number 3, which is moment. As in the case of simply supported beam, as we already know that when the UDL acting on the entire span of the beam, then we have the formula of bending moment is equal to WL square by 8, where W is the total load and L is the effective span of the beam. So we can calculate the bending moment by 25 into 8 square upon 8, and it is coming to be 200 into 10 to the power 6 Newton mm. Guys, for the calculation in the standard formulas, we have to take the values, we have to take the units in Newton mm, because in our codal values all our stress units are in Newton mm or Newton per mm square. So we have to take the values in Newton mm. The calculation will be easier. Now going to the step number 4, which is ultimate moment. Guys, as we all know about that, in the limit state method, we are working with the factor of safety. So we have to multiply with the factor of safety to the bending moment, and we will find out the ultimate moment. So for ultimate moment, factor of safety is 1.5, and our load is 200 into 10 to the power 6 Newton mm. So it is coming to be 300 into 10 to the power 6 Newton mm. But guys, in our formulas for the design process, we have to take the moment of resistance, which is mu, and we have the ultimate moment 300 into 10 power 6 Newton mm, and we can take it as a moment of resistance of the beam, because the moment of resistance is the resisting action of the structure by which it can bear the upcoming loads of the moments. And this 300 kilonewton meter is the applying moment so on the beam, and the same has to be resisted by the structure. And we are also using the factor of safety, so we are on the safe side. So our moment of resistance is equal to 300 into 10 power 6 Newton mm. Now we will use this moment for our further calculations. Now going to step number 5, it is for minimum required depth. It is effective depth. So as till now we are using the assumed depth, which was 400 mm. Now we are calculating the actual depth for the calculations, and which is the minimum depth, which will be the minimum depth, and the depth should not be less than this minimum required depth. So here's the formula. We have D is equal to mu upon q into b, where mu is the moment of resistance we have already calculated, and q is the another constant which depends upon the grade of concrete and type of steel, and its formula is 0.36 FCK XU max by D in brackets 1 minus 0.42 XU max by D. In this formula, FCK is the characteristic strength of concrete and XU max by D is the constant which depends upon the type of steel. And the RCC structures, we generally use three types of steel, which is Fe 250, Fe 415 and Fe 500. And the value of XU max by D for all these three types of steels have different. And in our calculation we are using steel of grade Fe 415, so the value of XU max by D for Fe 415 is 0.48, and in the case of 50 it is 0.53, and for Fe 500 is 0.42. So we will accept this value for XU max by D, and we can calculate the value of Q. It is 0.36 FCK. The grade of concrete is 30. XU max by D is 0.48, and 1 minus 0.42 into 0.48. So after the calculation, you'll have the value. It is 4.13, and the value of mu and b you already have. So here we calculate the D minimum. It is equal to the root 300 into 10 to the power 6 upon 4.13 into width, which was 150. So the minimum is equal to 300 4.13 into 150. It is 695.88 mm. But our assumed depth was less than this depth, and this is the minimum required depth, so we will adopt this depth for our further calculations. So let's go into this next step, which is step number 6, and it is for area of steel, AST. Here we have the formula determining AST. It is AST is equal to mu upon 0.87 Fi D minus 0.42 XU max. And from the relation of XU max by D is equal to 0.48, now we have the value of D, so we can calculate the value of XU max is equal to 0.48 into, we have the depth of 695.88, so the value of XU max is equal to, it is 335.6 0.46, and this is the formula for area of steel. Guys, there is no need to learn the complete formula in the cases of RCC calculations, because this they all these formula are linked together by the basic concepts of mechanics. So if you have the basic knowledge of mechanics, then you can easily create the formula for RCC calculation by your own. As you know that moment is nothing but load into perpendicular distance, and we know the load in case of stress. So stress is equal to load upon area. So if we have to find the area, so area is equal to load upon stress, and moment is equal to area into stress, and this is the load, and into perpendicular distance. So from here we can easily find out area is equal to moment upon stress into perpendicular distance. As you can see in this formula, this is our moment of resistance, which is moment, and this is a stress of steel, and this is a perpendicular distance from the neutral axis of the beam to the center of the tensile reinforcement. So it is the perpendicular distance. So it is easy to calculate or to create the formula by your own if you have the knowledge of basic mechanics. There's no need to learn the complete formula. Okay, so let's find out the area of steel, which is AST is equal to, we have the moment, which is 300 into 10 to the power 6 upon 0.87. Fy have 415, and we have the value of T is equal to 695.88 minus 0.42 into, the value of axiom axis, it is 335.46. So here we can calculate the area. So it is coming to be 1497.17 mm square. It is our area of steel. Now let's go to the next step. Is step number 7. It is minimum area of steel and maximum area of steel. Guys, it is a range of the minimum area or the area of steel which should required in the beam. So our calculated area should lie in between these two values, between minimum and maximum areas. It should not be less than the maximum area, and it should not be greater than the should not be less than the minimum area, and it should not greater than the maximum area. So according to the IS 456, we have the formula of minimum area of steel. It is a minimum is equal to 0.85 BD upon Fy. So 0.85 150 into the depth we have 695.88 upon Fy 415, and is 213.79 mm square, and A max is equal to 0.04 to P into overall depth. So here we have to take the overall depth of the beam. So let's take the effective cover be 20 mm, then D is equal to 695.88 plus 20, D is equal to 0.88 and 5, 11, 715.88. So approximately we are taking it as a 716 mm. Okay, so here we can find out the A max, 0.04 into 150 into 716. It is 4290 mm square. So our AST was 1497.17, and this AST is lying between minimum area and the maximum area, so this AST is adoptable. Okay, now our last step is to find out the number of bars. So number of bars is the total area of steel provided upon area of single bar. So here we have to assume the diameter of bar. So let's assume dia of tensile reinforcement B 25 mm, then area of one bar is equal to pi into 25 square upon 4. It is from the area of circle, so here we have pi into 25 square upon 4. It is about 490.87 mm square. So the number of bars will be ST, we have 1497.17 upon 490.87, and it is coming to be 3.05. So we are taking 3 bars. Thank you guys watching for this video. If you get benefit from this video, then please like it and share it. And if you have yet not subscribed my channel, then please subscribe my channel as soon as possible for regular learning.